Hopefully that wasn't too bad on these two questions right here, because it's stuff we've gone over before. Yeah, looks like number 1, W was 2, and number 2 just has no solutions on that one. Here's our 2 objectives for the day. I can find the missing side length of right triangles with the Pythagorean Theorem, and also I can determine if 3 lengths would make a right triangle. Take 1 minute, copy that down, please. So in the objective, it talked about a right triangle. Okay, so right triangle, let's try to make that line a little straighter. I don't know. I'm going to pretend like that's a straight line, and then this is a straight line, okay? Well, you'd make a triangle out of this, of course. And if those lines were straight, this would look a lot better, but you're going to end up with what we call a right angle right here, okay? Now, it's usually given this mark. A right angle is where that angle is 90 degrees. Why do they call it a right angle? I don't actually know, but I also actually don't care. That's just what it's called, okay? So this is a right triangle, and we're only concerned about that one angle being 90 degrees. That is how we will know that it's a right triangle. Now there's different words or different labels or parts of this right triangle, which is a very specific type of triangle. And they got the 2 sides that make up that right angle right there in orange. That's the red side, and what I have here is the purple side, okay? The red side is what we call a leg. The purple side is what we call also a leg. These 2 are legs. Why are they legs? I don't know. That decision was made long before I ever existed. So, the third side of this triangle is this is the long side right here. This is what we call the hypotenuse. Why is it called the hypotenuse? I don't know. I kind of assume it's Greek for the longest side of a right triangle, but I actually don't know that. So hypotenuse is the longest side of a right triangle. It's also the side length here that I've shown in green, but you see that that side length does not make up the right angle. Only 2 of those sides will make up the right angle. Those 2 are legs. The other side is the hypotenuse, and again, the hypotenuse is the longest side of a right triangle. So why is this important? Well, it's because of the Pythagorean Theorem. Okay, so let's take this stuff and look at it on the next. All right, so this is the Pythagorean Theorem. It states, it's a conditional statement, by the way, if you have a right triangle, like this one we have right here, then you take one of the legs and raise it to the power of 2. And if you took the other leg and raised it to the power of 2 and added those, you'd have the hypotenuse to the power of 2. So this would be stated as leg squared plus leg squared equals the hypotenuse squared. And that's actually, excuse me, that's pretty literal. So if you actually made squares out of those side lengths, the purple square and the red square areas would add up to the area of the hypotenuse as a squared. So you'll see it more like this later on. A squared plus b squared equals c squared. It's a pretty common math term that's used, and people look at it as though it's kind of nerdy, but trust me, it's not even close to the nerdiest thing that math people do. Okay? So, you're going to take these lengths, you'd square them, the red and purple ones, and if you squared the hypotenuse length, then adding those 2 together would equal the same as the hypotenuse as a squared. Yeah, in this formula right here, A is a leg, B is a leg, and C is the hypotenuse. Unfortunately, you kind of have to remember that as well. So yeah, this is a key part of our statements that we're making, is that when you see a right triangle, and let's say they don't give you a picture, but they say it's a right triangle, the longest side is always the hypotenuse. So it also kind of looks like this. C, remember, in this triangle, it's showing the C, here's the hypotenuse, A is a leg, and B is a leg, just like we saw in the last diagram. But again, if you made squares out of those, right, like I was saying, you'd have a red square here, and then you'd have a purple square here. If you added those 2 areas together, you can try this at home. We're not going to do it today. But if you added these 2 together, then you would get the green square. area. And some people find that interesting, but I find that most people don't. So that's why we're not going to do it as well. And just a little background on this one. I believe it was one of the U.S. presidents that came up with this. It's called a proof to show that it works. Of course, there's others, but they're pretty nerdy. So you understand, this is one of our mastery quizzes that we're going to be doing. You got to be able to know this stuff pretty good, because again, this is one of those where if you can't do this stuff, then the 9th grade teachers are like, please don't send them over here until they know this stuff, okay? So you got to be able to pass that quiz. It's mastery quiz on the grade, and well, I guess we may do some other stuff with it. What does this say? Round to the nearest thousandth if necessary. I don't know if we're going to need that. We'll see. All right, here's our first example. Okay? And here's what we know. That leg to the power of 2 plus leg to the power of 2 equals hypotenuse to the power of 2, right? Now, of course, you could show it as a squared plus b squared equals c squared. And in fact, they're using the c. And if you see it like this, then usually we should know that the c is the hypotenuse. But we can see also that it's not making up that 90-degree angle right there either. So we should know that it's the hypotenuse just based on what we know about right triangles. So we have two legs. This first one here, 3, that's a leg. So I replace the leg with 3. The other leg here is 4, so I replace that with 4. Now what I'm going to do is I'm going to square both of those, add them together, and it will equal c to the power of 2 as well, because c is the hypotenuse. So this sets up the formula that all we got to do to solve for c is just, well, solve this equation. So we'd say in my calculator I'd do 3 times 3, which is old 9er. And then I'd do 4 times 4, which is 16. Well, why didn't I add 3 plus 4 first? It's because of the order of operations. You got to do exponents first. And then I would add these two together, 9 plus 16, and I would know that it would be the same as the hypotenuse to the power of 2. And then from here, I'd say, well, 9 plus 16, that actually is 25, which equals the hypotenuse to the power of 2. So, like I was saying before, this 25 right here is the area of a square, but what we want is the side length on that, okay? So if the square had an area of 25 square units, then if we wanted the side length, like we've seen before, I would square root the c to the power of 2. But if I do it to one side, I got to do the other side. And what I end up here with is c, the hypotenuse. The square root of 25, we can put that in the calculator. Just push second x to the power of 2. And then type your 25 in there, then push enter. Now, I don't really need it because I'm just looking at the posters. And I can see that 5 to the power of 2 is 25. So working backwards, that means that the side length would be 5. So I see now that the length of the hypotenuse on this one is 5. So we can even put it up here. Now, this is interesting because you'll notice that there are no decimals for any of the 3 side lengths. These are all whole values. When this happens, we call these Pythagorean triples. So you'll see that vocabulary on the assignment today. Okay. So Pythagorean triple is where the values don't have decimals that repeat or terminate, or you could also see them that they do not have square roots in the answers. Which is, I don't know, it's pretty convenient. By the way, I believe on the assignment you're going to have to be able to simplify square roots as well. But we've done that before. I think it was the first lesson in this unit. So on this problem, again, the 2 side lengths that make that right angle are this one here in red and then this one here in purple. Okay, those 2 side lengths make up the right angle, which means they are also legs. So if we look at the Pythagorean Theorem, which tells us a leg to the power of 2 plus another leg to the power of 2 is the hypotenuse to the power of 2. And yeah, the hypotenuse is just the c value right here, okay? So I'll take the one in red first, that's 12. the leg, and then the leg that's 9, it's right here, and then the hypotenuse, we don't know. But I know if I took the two legs and squared them and added those values together, it would be the same as the hypotenuse as a power of 2 as well. All right, so this sets up an equation that all we got to do at this point is solve it. So I'd say 12 to the power of 2. I put this in the calculator, I get 144. I put 9 to the power of 2 in the calculator, I get 81. When I add these together, it will equal the same as the c, the hypotenuse, to the power of 2. So let's go ahead and add these two together. 144 plus 81, so that'd be 5, 4 and 8 is 12, 225. So this is going to be the same as our hypotenuse to the power of 2. Now, it is true that I just want the hypotenuse, though, not the hypotenuse to the power of 2. So, in order to make it just the hypotenuse, I'd have to square root it. Now, again, this is an equation, though, so if I do it to one side, I must also do it to the other side as well. So I take the square root of 225, which we can put directly into the calculator. And when I do that, I get 15. So that's the length of the hypotenuse right here, is 15. Now we don't know the units, but if it had units, we would label it. Now this is also known as a Pythagorean triple. What's a Pythagorean triple? It's where the three values of the triangle, a right triangle specifically, are all whole values like this, 9, 12, 15. Generally speaking, these will have decimals, or simplified, they'll include a square root, which none of these have. Okay, it's all just whole values, no decimals, no square roots. Boom, we're done. All right, here's this triangle, and we'll have to remember the Pythagorean theorem right here. A squared plus b squared equals c squared, where a and b are legs. So leg to the power of 2 plus leg to the power of 2 equals hypotenuse to the power of 2. And the two side lengths that are given, again, it's important to acknowledge where the right angle is, which I've highlighted in orange there. And so I'd say this can be a leg right here. Remember, the two legs make up the right angle, and this first one here is 8. So I would make that red leg 8. And then the other side length that makes up that right angle is 7 right here. Now just so you understand, while we've seen these ones that have the two legs, sometimes they're going to give you the hypotenuse, you're going to have to solve for the leg. That's coming, all right? So what are we going to do? We're going to take the two legs and square them, or to the power of 2. We're going to add those together, and that should equal the hypotenuse to the power of 2. Now that shouldn't be too difficult. We can put these directly into the calculator. I'd say 8 times 8, or 8 to the power of 2, which is 64. And then 7 times 7, or 7 to the power of 2, which is 49. And yes, we are going to add these, because the sum of those two will equal the hypotenuse to the power of 2. Now, for the addition, 64 plus 49, 113. Awesome. So that's 113 equals the hypotenuse, c, to the power of 2. But remember, we don't want c to the power of 2 in an equation like this. What we would like is just the hypotenuse by itself. Or that this is like saying, well, the area of a square is 113 square units, but we want to know the side length. So what do? We take that c to the power of 2 and square root it. But if I do it to one side of the equation, I got to do the other side right there. Right? So this would give me c to the power of 2. So I'm going to put this in the calculator. Let's see if I can find my calculator. That sounds good. This is just the square root of 113 right there. Okay. Now this is an exact answer. Of course, even though our calculators give us this square root of 113, if by chance it asked for a decimal on the assignment, then we would round this to the, well, I think it said the nearest thousandth, right? But you just push the double arrow button right above the enter button, and it will change it into a decimal for us. So as a decimal, it looks like, yeah, we'd have that 10.630 round to the nearest thousandth. And that would be our hypotenuse if it wanted a decimal rounded to the nearest thousandth. Yeah, so if by chance, if you have these switched as well, it's not going to matter, especially because of the order of operations, right? 7 to the power of 2 plus 8 to the power of 2 Yeah, you'd still get the square root of 113 there. All right, let's go over this one. So on this one, we have another leg here that's 6, and the other leg is 2. Okay, how do we know that? Because these two lengths make up the right angle right there. So let's take these. The leg of 6, that's my red one, and the leg of 2, that's the purple one there. The hypotenuse, yeah, we don't know that right now, so we're just going to use a C value there in its place, just like it does over here. But if I took the two legs and squared them, then added them together, I would get the same as the hypotenuse to the power of 2. So let's go and evaluate these. 6 to the power of 2 is 36. 2 to the power of 2 is 4. When I add these together, I'll have the hypotenuse to the power of 2 as well. So let's go and add these together. 36 plus 4, that's 40. This is the same as the hypotenuse to the power of 2, but we just want the hypotenuse. So it's at this point that I'd say, well, take the square root of c to the power of 2, which is just c. But I know if I do it to one side, I'm going to have to do it the other side as well. So I'm going to take the square root of 40. When I put this in the calculator, it's going to punch out 2 times the square root of 10. Now, that's an exact answer, but on the assignment, I believe if it shows something like this, it wants the answer rounded perhaps to the 10th. So we're just going to put this into the calculator as well. In my calculator, I got 6.3245, so I'll make that 325, rounded to the thousandth. I believe on the assignment it wants it rounded to the nearest tenth, so that'd just be 6.3. But either one of these will work, depending on how it asks for the answer on the assignment. Now, we've done this simplification before in the first lesson of this unit, but seeing it again shouldn't be too big of a problem. Again, you don't really have to simplify this by hand, square root of 40. Just put that in the calculator and you're done. All right, of course it's okay if our values have decimals. That shouldn't be a problem for us. And again, it does not matter which order you put these in, but I'm going to say the red one is the 0.8. Right there, that's our first leg. And then our second leg will be this purple one, we'll say 0.6. So the Pythagorean theorem says go ahead and square those, then add those values together, and it will be the hypotenuse, which is always represented by the letter C here to the power of 2. Well, you're going to have to put these in the calculator to solve these. 0.8 to the power of 2, I get 0.64. And 0.6 to the power of 2, putting in the calculator, 0.36 right there. So that evaluates the exponents, which means when we add these together, we should have the hypotenuse to the power of 2. Well, let's go and add these together. So again, you can use your calculator to do that. 0.64 plus 0.36, I get 1. You can put 0.0 if you'd like. It's not going to make any difference, but that is our hypotenuse to the power of 2. So this is like a square with an area of 1. But again, we just want the side lengths of that square. So if I just want the side length from a power of 2, I would square root it. But if I do it to one side, I got to do it the other side as well. The square root of 1 is 1. And that's done. All right, now this triangle has been kind of rotated a little bit. Perhaps we may think so anyways, but it shouldn't matter. Again, we got the two legs. First one here is 5, and then the other leg here is square root of 11. That's not a problem, and then the hypotenuse still is unknown on this one. So that's our C value. The red leg length is 5. The purple leg length is square root of 11. So again, we're going to solve this with the Pythagorean theorem. Square the two legs, add them together, and it's the hypotenuse as a square as well. So let's put this in the calculator. 5 to the power of 2, we should know is 25. The square root of 11 to the power of 2, though. If you put this in the calculator, make sure you get out of the exponent mode or the square root mode before you put the square in. At least that's the way that it's written. And what do you get? You should get 11 out of that, okay? Now this is equal to the hypotenuse to the power of 2. And some of you may ask, well, why is this square root of 11 to the power of 2 11? It's because square roots and powers of 2, they essentially cancel each other out, okay? It's just a phantom 1 exponent, which is why we just end up with whatever's inside of the square root 11 right here, okay? So this is something that I can put directly into the calculator. I would combine 25 and 11. 25 plus 11 is 36. And this is equal to c, the hypotenuse, to the power of 2. Well, we don't want c to the power of 2, we want c. So I would square root it to get c, and I do. But this is an equation, so if I do it to one side, I got to do the other side. Square root of 36, put that in the calculator, 6. That's our answer right there. That means the hypotenuse, c, is 6. All right, we'll use the Pythagorean theorem to solve for this leg. And yeah, this leg right here is given as 0.12, so I'd replace that leg, red, that I'm using, 0.12 right there. Now this length right here that's given to us, we got to be careful because remember that we got to put these values where they go in the Pythagorean theorem. So 0.2, see how it's not making up that right angle? That means it's a hypotenuse right there at 0.2. Which means this leg right here, B, is unknown. So I'm just going to use B in for that purple leg. And now I'll finish the Pythagorean theorem. Let's square the legs, add them together, and that'll be the hypotenuse to the power of 2 as well. All right, and all these values, even though they're decimals, I'm just going to put them into my calculator to solve for them. All right, so 0.12 to the power of 2 in my calculator shows 0.0144. And 0.2 to the power of 2, 0.04. Now everything else stayed the same. We still have b to the power of 2, needing to add to that 0.0144. But again, this is just an equation to solve. We're going to solve for b to the power of 2, which means I don't want that 0.0144 added to the b to the power of 2. So I'm going to have to subtract it from both sides of the equation, because that's our principle of equality, right? If you do it to one side, you got to do the other side. So that's going to zero that out just like we want. We'll drop our b to the power of 2, which equals, let's put this in the calculator, so 0.04 minus that stuff. I got 0.0256. Well, we don't want b to the power of 2, we just want b. So how do I make that power of 2 go away? Just square root it. But again, if I do it to one side, I got to do the other side. So I got to take the square root of 0.0256, enter, and I got 0.16. So that's my b value, one of the leg lengths right there, 0.16. Yeah, and that's done. So yes, it will ask you on the assignment to solve for legs sometimes and not hypotenuses. Also keep in mind that on the assignment, it's possible that it may not give you a diagram like this, but it will say this is a leg length, this is a leg length, and a hypotenuse. Find whatever the missing value is. All right, for this one, we got a leg and a hypotenuse, right? So let's go ahead and look at our Pythagorean theorem here. And this leg, again, doesn't matter if you make it the red or the purple one. I'm just going to start with the red one. So this leg is 4. And then this other length right here, the square root of 41, this is the hypotenuse because we see that it does not make up that right angle right there. Okay? So the hypotenuse, yeah, I mean, I can actually put it in as the square root of 41 right there. Okay? Now let's go ahead and square those two, because when we do, if you were to take that leg of 4, raise it to the power of 2, and then the other leg, I'll just show it as b. Well, I guess they're using a right there. It doesn't really matter which is which. So I'm going to use base a to the power of 2, because this is the other side length of this triangle that makes up that 90-degree angle. If I squared it, then it would equal the hypotenuse to the power of 2. So solving this one is just like solving an equation with, well, exponents. And that's okay because we know how to undo exponents. And that would be with roots, particularly in this case, square roots. So I'd say 4 to the power of 2 in my calculator, 16. And then I type in 41, square root of 41 to the power of 2. Now make sure you're out of the square root mode before you square that, because the answer is 41. All right, square like this 2 and this square root, they pretty much undo each other. It becomes an exponent of phantom 1 right here, which you'll learn more about next year. So this is, if I add the 16 to the other leg, a to the power of 2, then it would equal 41. Now, of course, we're solving for a leg on this one, a, so I don't want anything added or subtracted to it, so I'd get rid of that 16 right there and by get rid of, I mean make it a 0, so I'm going to subtract 16 here. 16 minus 16 is 0, that's what we wanted. And now I have a to the power of 2 equals 41 minus 16, 36, 31, yeah, 25, right? Yep, thank you. 25, and we've seen this before, right? This is like saying, well, this square, if we made a square out of a here, would have an area of 25. Well, we don't want the area of the square. What we really want is the side length. So I'd square root a to the power of 2 to get a, and then this would equal also, remember the principles of equality, if you do something to one side, you should do it to the other side. So I take the square root of 25, which is 5. Bam. Now this one had the square root of 41 as one of the side lengths. Some people are intimidated by that, but you see, since we're taking the square of that, it just gave us the 41 right there. And the more you start to see this, the more you'll get used to it. Maybe that's a good thing or a bad thing. I'll let you decide. But that's an easy calculation. Eventually you'll just see, well, I don't really need to put this in the calculator. I just know whatever's on the inside is the actual value after I square it. All right, here's another problem. And sure enough, we have this 10 right here. That's a leg because it makes up the right angle. So I'm going to replace that leg with 10. How do we know it makes up the right angle? Because there's our right angle, right? It's one of the sides that make up that right angle in orange. Now this other length right here, 10 to the power of 10 times the square root of 2, that's our hypotenuse. Well, how do we know that? Because it's not making up the right angle, right? These two sides make up the right angle. The one that doesn't is the hypotenuse. So that's 10 times the square root of 2 as my hypotenuse, okay? The other leg is x. So we just don't know what x is, but we're going to solve for it. All right, but that's another leg right there. So I'm going to take 10 to the power of 2, x to the power of 2, add those together, and this will equal this hypotenuse in green to the power of 2. Now that's 10 times the square root of 2. Just to be careful in our calculators, let's put that in parentheses right there, and then raise it to the power of 2, okay? Because if we don't, sometimes we may put it in wrong, or, well, the calculator may do it by the order of operation. So if we put parentheses around it, then we don't have to worry about that stuff. Now 10 to the power of 2, we already know, or should know, is 100. But 10 times the square root of 2 to the power of 2 in parentheses, that should give us 200. Okay, so 100 plus x to the power of 2 equals that 200 in green. Again, we're just solving for the x right there, so I got to get rid of that 100, zero it out, right? So I just have to subtract it. But if I do it to one side of the equal sign, I got to do the other side. So that's going to zero that out. I'll drop this and make it x to the power of 2 now equals 200 minus 100. Yeah, just 100. But we don't want x to the power of 2, we just want x. So let's square root that. But if I do it to one side, I got to do the other side. So square root of 100, 10. So this value also 10. And then this other leg, find the value of x using the Pythagorean Theorem, leave your answer in simplest radical form, if we need to. Right? Now this one, here's the unique thing about this one is the two side lengths that are unknown are both legs right here, right? However, what it's showing us is that it's the same value for both legs. So when I put this into the formula, our Pythagorean Theorem, one of the legs is x, but as it turns out, the other leg is the same x. So it's just x's right there. And then the hypotenuse, right here, that's a 20. Because it's the side that does not make up the right angle. So I'm going to square the two legs, add those together, and this would equal 20 to the power of 2. So only one calculation to perform here, 20 to the power of 2 in the calculator, 400. And then we got x to the power of 2 plus x to the power of 2 equals that 400. Now if we go back to what we call like terms, we have two x to the power of 2's on this one, right? I got 1x to the power of 2 and 1x to the power of 2 there. Both of these are coefficients. That's kind of a word we haven't used in a while. But if I combine these, how many x to the powers of 2's would I have? I'd have 2 of them. So this equals now 400. Okay, so in solving this now, I'd say, well, let's divide both sides by 2 to make it just x to the power of 2, which equals 400 divided by 2 is 200. But we just want one of those x's, because that's what it said right here, right? Find the value of x. So I'd say, well, let's just square root this business right here. That'll give me just the x, because remember, the power of 2 and the square root will essentially undo each other. So square root of 200 would be 10 times square root of 2. In the calculator anyways. What is that as a decimal? That's what I don't know. Square root of 200, yeah, 10 times square root of 2. Double arrow button shows this value as a decimal. And again, it should specify which it wants on the assignment. I got 14.142135562. So 142, if I rounded this to the nearest tenth. Either one of these work. Well, let's solve for x on this one. And you can see that x itself is a leg of this right triangle. Hopefully you can see that. Because the 2.1 makes up this side length. And the x is this side length. And those two make a right angle shown with this symbol. I do understand that sometimes they're going to be like, hey, solve for the missing length of this triangle. But they may not show the right angle. If they ask for something like that, either a leg or a hypotenuse, then we get to assume that this would be a right angle. But just know that sometimes they won't show that all the time, okay? So let's look at the Pythagorean Theorem. There it is. Found it. It's leg to the power of 2 plus leg to the power of 2 equals hypotenuse to the power of 2. And the leg that I have, I've made it red in 2.1. The x is the other leg, so I'll just put the x there. Now, sometimes, again, like we've seen in previous problems, is they'll use either a or b. It doesn't really matter. But the hypotenuse I see on this one is the other length, which is 2.9. Well, the Pythagorean theorem says if we take the two legs and square them and add those together, then it would equal the hypotenuse as a square as well. So let's go ahead and put these into the calculator. Let's see, 2.1 to the power of 2. Enter. I got 4.41. Yeah. 4.41 there. And then I go to my calculator and I put 2.9 to the power of 2. Enter. I got 8.41. Right now, when we add that 4.41 to the x, the other leg, to the power of 2, then we get 8.41. But again, we're solving this like an equation. So I would need to subtract at this point the 4.41 from the left side of the equal sign. But if I do it to one side, I got to do it to the other side as well. Why subtract it? Because we want it to be 0, and it is. Why do we want it to be a 0? Because it's a phantom value. It's there. We just don't want to look at it all the time because it's kind of ugly. So I'd say x to the power of 2 here equals 8.41 minus 4.41. I get 4. That's what I got. But we don't want x to the power of 2. We just want the x value, as shown right here. So I would take the square root of that x to the power of 2. But if I do it to one side, I'd have to do the other side with our principles of equality. That's just going to give me x. Well, x equals the square root of 4, 2. X equals 2. Done. Now, it looks like Megan made some kind of mistake. Let's find out where. By the way, I don't know who Megan is. It's just part of the problem. So it says here's the 5 and 13. And so what did Megan do? She took the 5 and raised it to the power of 2 and 13 to the power of 2, which you're supposed to do. But we can see clearly that the 13 here is a hypotenuse, which I've been using green. And I know that's not a straight line, but I did my best, which means the 13 really should be the C value, not the B value. It's not a leg. It's a hypotenuse. So, yeah. Sorry, Megan. The rest of this is false. Okay? Well, I mean, this one is too, but by the way, if you put a 13 here and then solved it, you'd get the b value, which is really what we want here, is 12. And again, that makes a Pythagorean triple of 5, 12, and 13. This is a pretty common mistake. A lot of students, well, we're getting used to it anyways. They'll misplace legs as hypotenuses or hypotenuses as legs. Just be careful on that one. Make sure you know which length is which so that when you put it into the formula, you're doing it correctly. So Raphael was asked to solve for the length of the hypotenuse in a right triangle with legs that have side lengths of 4 and 5. His work is shown below. He made a mistake solving. Let's find out what it is. Well, now this one's not as common as that last one, but 4 to the power of 2 is 16. 5 to the power of 2 is 25. And yes, 4 and 5, it said right here, they are leg lengths. So they're in the correct positions. It's common for students to put maybe a hypotenuse where a leg goes or a leg where the hypotenuse goes. Be careful on that. So what did he do? He says 16 plus 25 is 41. That's correct. But remember that does not change c to the power of 2. It'll still be c to the power of 2 right there. So that's kind of a mistake. And so the final answer here, you just square root both sides here. That would give you c is just the square root of 41. That's better. That's a quick fix right there. But this mistake does happen from time to time with students' work. All right, now the converse of the Pythagorean theorem. Converse just means that we're going to do it backwards. Okay? So the converse, remember the Pythagorean theorem, right? All right, there's our Pythagorean theorem at the bottom. If you have a right triangle, then leg to the power of 2 plus leg to the power of 2 equals hypotenuse to the power of 2. Well, the converse is just going to switch the if and then statements. So it's still an if-then statement, still conditional. It's just backwards, right? If you found that a leg to the power of 2 and another leg to the power of 2, and you added those together, those two legs to the power of 2's squared, then as it turns out, you'd find it would equal the hypotenuse to the power of 2. It's a long word. Then you have a right triangle. Use a symbol for that triangle because it's a big word. All right, see how that switches the if-then statement? If you find that you had 3 side lengths, then the leg to the power of 2 plus the other leg to the power of 2 equal the longest value to the power of 2, then you'd have a right triangle. So that's something else that you need to understand about these right triangles is the longest side is always the hypotenuse. That's going to be crucial because in the following problems, they're not going to give us a picture of a triangle. They're only going to give us 3 side lengths, and they're going to say, does it make a right triangle? Well, that's where we use the converse of the Pythagorean theorem for that. All right, so will these 3 side lengths make a right triangle? It's wording it different, but that's pretty much saying the same thing. Will these 3 side lengths make a right triangle? Now, do remember, and sometimes they don't always put these in order, so you have to look at these and think, well, which is the longest side? Because the longest of the 3 values, the biggest of the 3 values, is always the hypotenuse, okay? Which means in this case, I would say that 11 and 60 are the 2 shorter sides, and 61 is the c value, all right? So the 2 legs we know are 11 and 60. We're going to square those and add them together and see if it equals the hypotenuse, which is 61, to the power of 2. So we don't know if this is true yet, but we're trying to find out. So I'm going to put a question mark over the equal sign. Well, I put an equal sign right there too. That's supposed to be plus. So I can put this into the calculator now. Okay, 11 to the power of 2, that's 121. 60 to the power of 2 is 33,600. I don't know what 61 to the power of 2 is, though. Let's put it in the calculator and find out. 3,721. There we go. Now, if I add the two legs together, I should get that green value, 3,721. And when I do, 121 plus 3,600, yeah, 3,721. So again, this is more of a question. Does that equal 3,721? Because if it does, then this would be a right triangle. That's true. Right there, okay? Now, if by chance we added the two legs together as squares, and we got not the same as the green value, then we'd say it is not a right triangle. It would make something else, perhaps not even a triangle. We don't even know, nor do we care, because we only want to know if it will make a right triangle. That is all. So the answer, the final answer on this one is just yes. Now, do the side lengths given below satisfy the Pythagorean theorem? It's really saying, will these three side lengths make a right triangle? Let's find out. All right, so I'm going to take our Pythagorean theorem. Now remember, of the three side lengths, the longest one has to be the hypotenuse. And right here, the longest of the three sides is 6. So my hypotenuse for these three would have to be 6. But remember, from time to time, they won't list these in order from least to greatest, like they are on this one. So the first leg I have there in red is 2. Second leg is 4. Now, if we square those two legs and add them together, we should get the hypotenuse as a power of 2. And since we don't know if this is true or not, I'm going to put a question mark over the equal sign because I don't know if that's true. But I do know that 2 to the power of 2 is 4, 4 to the power of 2 is 16, and 6 to the power of 2 is 36. When I add the two legs together as squares, I get 20. So does 20 equal 36? No, it does not. Yeah, this one's clearly false. Which means that would this satisfy the Pythagorean theorem? Would it make a right triangle? No, it would not. Well, these three side lengths make a right triangle. Well, let's find out. Let's use the Pythagorean theorem here. And so, again, this one shows that the side lengths are not in order from least to greatest, which means 14, that's one of the legs. 48 would be the other leg, and then 50 here is the hypotenuse. Okay, it's important to know that the longest side is the hypotenuse. So I'd say, well, one of the legs is 14. The other leg is 48. We're going to square those. Add them together, and it should equal the hypotenuse, which is shown as 50 to the power of 2. So let's put these in the calculator. 14 to the power of 2. I'm actually just going to use the poster there, 196. I don't have 48 on the poster, so I have to put this in the calculator. 48 to the power of 2. Enter 2,304. And then 50 to the power of 2, 2,500. So let's add these together and see if it equals that 2,500. So yeah, we are checking to see if this is true. So a question mark over the equal sign, because we don't know yet. And let's go ahead and add these together. So 4 and 6 would be 0, carry the 1, that's another 0. It's looking pretty good. 3 plus 1 is 4, plus another 1 is 5, and then the 2. Yep, this looks like it is good. 2,500 in blue from the addition equals the 2,500 in green from the hypotenuse. Yes, this is a true statement. Because the two are equal, which means that yes, these three side lengths would make a right triangle. So we're seeing that the Pythagorean theorem is really just a formula that we have to solve, just like we did with volume and maybe back in 7th grade with surface area, okay? Now the square root of 10, I'm just looking at the poster up there, is about 3.162, which means that's bigger than 3, right? Which means that the square root of 10 would have to be our hypotenuse. 1 can be a leg and 3 is a leg. Doesn't matter which one you make it, okay? But our Pythagorean theorem, leg to the power of 2 plus leg to the power of 2 equals the hypotenuse to the power of 2. Okay, so the one leg is 1, the other leg is 3, and then the hypotenuse is the square root of 10. So let's go and square the two legs, add them together, and maybe it will equal the hypotenuse to the power of 2. I'm just going to put that in parentheses, just so we kind of get used to that for now. 1 to the power of 2, 1 times 1 is 1. 3 to the power of 2, 3 times 3 is 9. When I add these together, for the square root of 10 in parentheses, yeah, I get 10 on that, right? And yes, 1 plus 9 is 10. Does 10 equal 10? Yes, it does. Okay, so I should have shown that question mark on the equal sign there. But yes, that is true. So would this make a right triangle? Yes, it would. Well, these three side lengths make a right triangle. Well, that's what we're going to find out. So I don't know what 2 times the square root of 5 is. I'm just trying to determine which of these three side lengths is the longest. So I'm going to put this in the calculator. Type 2 times the square root of 5, enter. And I got to push the double arrow button there to change it. So it's 4.47-ish, which means it is the longest side. Okay. So that helps me to determine which of these is the hypotenuse. And clearly, 2 times the square root of 5, which is approximately 4.47213595, is the hypotenuse. There's our hypotenuse right there. So 2 is a leg length, and 4 is also a leg length. So 2, I'm going to put that in for the leg. 4 is another leg, and then the hypotenuse is shown as 2 times the square root of 5. Right? So if I took the 2 and squared it, and the 4 and squared it, added those together, it would equal the hypotenuse, 2 times the square root of 5 to the power of 2. Now, since we're going to be putting this in the calculator, I would recommend using parentheses around 2 times the square root of 5, so that the calculator knows you want to square all of that, and not just the square root of 5. That's a kind of a computer programming thing that's put into the calculators. Okay? So on my calculator, I push 2 to the power of 2 is 4. 4 to the power of 2 is 16. Actually, I'm just looking at posters. 4 plus 16. Now, let's see. What does this equal? 20. Right there. That's what I got. And what do I know? I do know that 4 plus 16 is 20. But does 20 in blue equal 20 in green? Yes, it does. Because that's what we're actually seeing, if this is actually equal. And yeah, that's a true statement. Which means that yes, these three side lengths would make a right triangle. Well, these three make up a right triangle. Let's find out. Here's our Pythagorean theorem. So on this one, 8 is the longest side, which means it's the hypotenuse. 5 and 6 are shorter, so there are legs. Doesn't matter which of the two you say is which. So the first leg I have is 5, the second leg is 6. My hypotenuse is 8. Let's square the two legs, add them together. That would equal the hypotenuse to the power of 2. And these are all whole values, so we should kind of know these values. 5 to the power of 2 is 25. 6 to the power of 2 is 36. You can always use your calculator for these as well. 8 to the power of 2 is 64. Let's add these together and see if it actually is equal. So 25 plus 36 is 61. Now, this is pretty close, right? 61 is pretty close to 64. But no, they are not actually the same. So this is false. Oh, gotta learn how to spell better. False. Since that is false, this does not satisfy the Pythagorean theorem or make a right triangle. So there's our objective again. I can find the missing side length of right triangles with the Pythagorean theorem. I can determine the three lengths would make a right triangle. So again, that second objective there is just the converse of the Pythagorean theorem. That's all.